Well, hello and welcome to our webinar this month. I'm Tom Sandry, Director of Workforce Development at Vector Power, and in this month's webinar, we're going to go ahead and talk about power factor, dissipation factor testing. So, without further ado, let's get started. Most electrical equipment failures are the result of insulation deterioration. Dissipation factor or power factor testing is one of the most effective and common ways to detect insufficient electrical equipment insulation. The test enables technicians to detect equipment insulation problems without making an internal visual inspection. Now, technicians that can properly perform and evaluate the results of power or dissipation factor tests can predict and prevent the failure of medium and high voltage transformers, circuit breakers, bushings, reclosures, switches, cables, lightning arresters, liquid insulation, potheads, rotating machines, and voltage regulators, just to mention a few items. Now, the intention of this webinar is to guide you in the appropriate method of making dissipation or power factor tests and also capacitive measurements on power apparatus and to assist in the interpretation of test results that are obtained. So far we stated, most failures of electrical equipment are the result of a breakdown in the insulation system, and dissipation factor or power factor testing is an effective way to detect defective electrical equipment insulation. Dissipation factor is the ratio of the capacitive or the charging current, measured in voltamperes, to the resistive or the leakage current, measured in watts. It is a means of measuring insulation integrity, since the smaller the dissipation factor, the better, or the more efficient the insulator. Insulation may be deteriorating, however, the equipment may not fail for some time. Although this condition presents a serious hazard, if deteriorated insulation is detected before failure, it can often be reconditioned instead of being replaced. This allows corrective action to be taken during a planned outage before extensive equipment damage results from an insulation failure. Dissipation or power factor testing also makes it possible to detect equipment insulation problems without making an internal visual inspection. The result is a significant decrease in maintenance costs and downtime. This testing is one of the best testing techniques for a predictive and or a preventative maintenance program. Dissipation or power factor tests can detect the presence of poor insulation even if there is a layer of good insulation in series. DC tests usually show a high insulation resistance under these conditions. At a given voltage, the charging current and the dielectric loss increase as the quantity of insulation increases. However, the ratio, dissipation or power factor, remains the same no matter how much insulation is present. This makes it possible to establish simplified test values for various types of insulation. Dissipation or power factor testing provides a measure and evaluation of the overall condition of medium and high voltage AC apparatus insulation under simulated normal frequency operating conditions. This is independent of the duration of the test. Now, DC tests do not simulate normal insulation operating conditions. Furthermore, the results are affected by the duration of the test. Dissipation or power factor tests provide a benchmark which may be compared over time in an organized manner and are used to identify any trends on apparatus insulation. It provides a more complete picture of overall insulation conditions. Used in conjunction with capacitive measurements, it provides comprehensive data of the nature of the insulation. Now, let's talk briefly about capacitive charging current and dielectric material. Capacitive charging current refers to the current that flows when the potential of an electrode changes, causing the amount of charge stored in a capacitor to change. Dielectric material refers to nonconductors or insulators in which an electric field can be sustained with a minimum dissipation of power. Unlike metals, no electricity flows in dielectrics when they are placed in an electric field. Instead, dielectric polarization, as we see here, occurs. When a dielectric is placed in an electric field, electric charges do not flow through the material as they do in a conductor, but only slightly shift from their average equilibrium position, causing dielectric polarization. This produces an internal electric field, reducing the overall electric field of the dielectric. Now, an important consideration for a dielectric material is its ability to support an electrostatic field while dissipating minimal energy in the form of heat. This dissipated heat or energy loss is known as dielectric loss. The lower the dielectric loss, the more effective the substance is as a dielectric material. Another consideration is the dielectric constant, which is the extent to which a substance concentrates the electrostatic lines of flux. Substances with a low dielectric constant include a perfect vacuum, dry air, and most pure dry gases, such as helium and nitrogen. Materials with moderate dielectric constants include ceramics, distilled water, paper, mica, polyethylene, and glass. Metal oxides in general have high dielectric constants. So let's do a little comparison here of a dielectric versus an insulator. Dielectrics can develop an internal electric field which nullifies the externally applied voltage, while insulators do not develop an internal electric field. Dielectrics are easily polarized and can store charges. Insulators actively obstruct electricity. Dielectrics contain relatively weak bonds with atoms. Insulators contain strong covalent bonds. And dielectrics mainly used in capacitors, power cables, transformers, and resonator oscillators, while insulators used in high voltage line systems and electrical appliances to prevent users from getting electric shocks. Now, insulation systems associated with many types of high voltage power apparatus and devices often consist of a mix of non-homogeneous component parts. As such, a complete and highly accurate schematic representation of an apparatus insulation system may be quite complex and difficult to compose, perhaps consisting of several resistor and capacitor elements arranged in many various ways. For discussion and analysis, it is convenient to represent an insulation specimen by a single capacitor combined with a single resistor. The capacitor element represents the specimen's fundamental capacitance, example, its ability to store electrically separated charges, while the resistor element represents the dissipation loss in the insulation when voltage is applied. As in this slide, there are two possible ways to combine a capacitor and a resistor. The capacitor. Two conducting plates with an area of A separated by a dielectric with a thickness of d, and a dielectric constant represented by epsilon. So the formula for capacitance, or mathematical representation of capacitance, is the capacitance equals the area multiplied by the dielectric constant divided by 4 pi times the distance between the plates. Now, based on this mathematical equation, Michael Faraday discovered that when the plates between a capacitor were filled with an insulating material other than vacuum, the capacitance would change. Dielectric constant is the ratio of the capacitance of a capacitor using that material as a dielectric compared to a similar capacitor that has vacuum as its dielectric. The dielectric constant of a vacuum is 1. All other dielectric constants are referenced to this standard. In this example, we see that if we were to change the dielectric material to oil, the capacitance would increase. This is because oil has a higher dielectric constant compared to vacuum. Here we show a chart showing some common dielectric constants of various materials, ranging from vacuum, by definition a dielectric constant of 1, dry air, which virtually has a dielectric constant of 1, polyethylene or XLPE, paper, mica, porcelain, oil, and water at 20 degrees Celsius. Now, kind of in your mind, think of the dielectric constants as being the ingredients in an insulation recipe. Tuck that away in your mind right now, and we'll kind of elaborate on that concept in a moment. So, let's look at a typical insulation system. Now, as I stated, we can think of the dielectric constants as the ingredients in the system's recipe. Here we are given 3 dielectrics in series: oil, porcelain, and paper. Adding the dielectric constants of each material gives us a total dielectric constant of 0.894. Now, let's change the ingredients. We will replace the oil with air. Air, having a lower dielectric constant compared to oil, results in the total dielectric constant of the insulating system go down. If the dielectric constant decreases, the calculated capacitance decreases, and thus the total current decreases, since there will be less capacitive charging current. All right, let's look at a practical application of this knowledge. The hot collar test is a part of the procedure in the dissipation or power factor testing of a bushing. When the test is done on a transformer, the test connections are on the transformer's bushing, and the test includes the transformer winding and the bushing. To measure only the dissipation or power factor of the bushing, we put a circular ring which acts as a connector around the bushing, a hot collar, which we connect to one side of the test set and the other side to the top of the bushing. In this manner, we can measure the dissipation or power factor, capacitance, and leakage current of only the bushing. We make 3 sets of measurements starting at the top of the bushing, working our way down, and render the results that are shown here. So, starting at the top, we take our first set of 3 measurements on each bushing, and here we're going to focus on capturing the leakage current. We go to mid-bushing, repeat the hot collar test, render the results shown, and finally, at the lower portion of the bushing, we repeat the test a 3rd time, once again capturing the leakage current from the test set's measurements. Now, What conclusion can we draw from the leakage current readings obtained and shown here on this slide? Take a moment, review the readings taken at each hot collar position. Using the practical knowledge that we just learned, what can you conclude from this data? Did you conclude that the oil level in the H3 bushing is somewhere between the locations used for the hot collar test number 2 and 3? As we can see, the leakage current on bushing H3 drops considerably compared to bushings H1 and H2 as we move up the bushing. The most plausible cause would be the oil being replaced with air. The lowering dielectric constant would result in a decrease of capacitance and thus a decrease in the current readings obtained. Now, let's review dielectric loss and what might cause dielectric losses of a material to change during its life. Dielectric loss is the time rate at which electric energy is transformed into heat in a dielectric when it is subjected to an electric field. The heat generated is given in terms of watts. Over time and aging, contamination and deterioration add to the normal losses of a material. Dielectric loss quantifies a dielectric material's inherent dissipation of electromagnetic energy, example, heat. It can be parameterized in terms of either the loss angle delta or the corresponding loss tangent of the angle delta. Both refer to the phasor in the complex plane whose real and imaginary parts are the resistive loss component of an electromagnetic field and its reactive or lossless component. A dissipation or power factor measurement circuit commonly views the specimen under test as a parallel capacitor resistor network. This equivalent circuit is repeated here, showing the various parameters of current with respect to the applied test voltage, where V is the test voltage, I sub T is the specimen total current, I sub C the capacitance or quadrature of the total current, I sub R the resistive or in-phase loss component of the total current, C sub P the equivalent parallel capacitance of the insulation specimen, and R sub P the equivalent parallel resistance of the insulation system. The resistor element of the equivalent dielectric circuit shown represents the watt loss dissipated in the insulation when a voltage is being applied. R sub P represents that which is generally considered undesirable in a dielectric. It should be recognized that a certain amount of measurable loss is normal for most dielectrics, and therefore the existence of loss per se does not necessarily suggest an operating hazard. Now, here we can see the relationships between current, capacitance, and dissipation or power factor. In an ideal insulating system connecting to an alternating voltage source, the capacitive current, or I sub C, and the voltage are in perfect quadrature with the current leading. In addition to the capacitance current, there appears in practice a loss current, the I sub R, in phase with the voltage as shown in this slide. The current taken by an ideal insulation, no losses, I sub R equaling 0, is a pure capacitive current leading the voltage by 90 degrees, or theta equals 90 degrees. In practice, no insulation is perfect, but has a certain amount of loss, and the total current, I, leads the voltage by a phase angle, or theta is less than 90 degrees. It is more convenient to use the dielectric loss angle delta, where delta equals 90 degrees minus theta. For low power factor insulation, I sub C and I are substantially of the same magnitude, since the loss component of I sub R is very small. Now, the power factor is defined as the cosine of angle theta, which also equals the sine of delta, which basically equals the resistive current divided by the total current. And the dissipation factor is defined as the cotangent of theta, which also equals the tangent of the angle delta, or more simplified, it equals the resistive current divided by the capacitive current. Now, to help us in understanding the operation of the test set, it's important to consider the relative positions of the test set's power source. For example, the 10,000 volt winding of the test set's high voltage transformer, the measuring circuit, and the specimen being tested with respect to the test ground and the low voltage measurement leads or measurement channels. Test sets that perform the dissipation or power factor measurement can utilize two low voltage measurement channels or leads and also a ground lead simultaneously. Although there are several manufacturers of dissipation or power factor test systems, we will use the Doble Model M4100 as our basic model in this presentation today. Now, to help us better understand the test modes and measurement process, let's review some basic laws of electricity. A difference in potential must exist between 2 points for current to flow. Current always returns to its source, and current always takes the path of least resistance, but current will be on each path. All right, now, Kirchhoff's current law states that all current leaving must return. Therefore, all current leaving the test set through the high voltage lead must return to the unit, either through the low voltage test lead, the red or the blue lead shown here, or the ground lead. Now, internal to the test set, the test leads are connected to either the meter or the guard. Test leads connected to the meter will be measured, and test leads that are connected to the guard will not be measured. By specifying a test mode, the user can choose to measure the red lead, the blue lead, the ground lead, or any combination, any two or all three. Test modes are selected in the Doble Test Assistant Field or DTAF software and instructs the test set which test lead ports to connect to the meter and which test lead ports to connect to the guard circuit. So again, going back to our slide here, we would see our ground lead connection, our low voltage measurement channels, either red or blue, our high voltage lead, which basically provides the source test voltage from the instrument's transformer. All right, so looking at the different test modes. With the analyzer in GST ground, RB, the low voltage leads are brought to ground potential. Thus, the low voltage leads may be used to connect ground to a specimen's terminal. And as we kind of see here in the slide, if we apply voltage, we would create a current flow going through CA, CB, CC. In the GST ground, any GST test, ground is always measured. So GST ground, and then representing R and B, basically says all three are going to be measured. As we again see in this slide, all three connections are brought through the meter, and the total current that we would be measuring on the test set would be the sum of current I sub 1 plus current I sub B plus current I sub C. Now, with the analyzer in the GST guard, the red and blue, the low voltage leads are connected to the test circuit guard. Get ready to compare the configurations that we're going to show on the next two slides, and note that both are grounded specimen tests, or GST mode. That is, both circuits measure the insulation between the high voltage test cable and ground. The single difference between the next two slides will be the position of the low voltage leads with respect to the measuring circuit. So again, here as we apply the potential, we establish a current flow through CA, CB, and CC. But in the guard red and blue, we see that the red and blue measuring channels are now routed to the guard. They bypass the meter and are not measured. Therefore, our measurement on the test set would be only the current flowing through the ground channel, or I sub C in this example. Okay, so here again we see the GST. We're going to guard the red, meaning we will not measure any current coming in on the red lead, and we will ground B, or the blue lead, which basically means that we will measure any current coming in on the blue lead. So again, our results in this would be the measurement of I sub B plus I sub C, and we would guard and not measure the I sub A. Once again, a GST guard the blue and ground the red. So again, we will measure red. In a GST test, ground is always measured, so we will measure I sub A and I sub C, and we will guard or not measure the I sub B. With the analyzer in the UST measure red or blue, the only input to the measuring circuit is through the low voltage leads. Observe that the test set guard and ground are common in the UST mode. Thus, current and losses to ground are not measured in any of the UST measurement modes. So, as we show here, we apply potential, and we only measure what's coming in on the red and blue channels. So our measurement is I sub A plus I sub B. Ground, anything coming in on the ground lead, is never measured in an ungrounded specimen test mode. All right, so here we show the UST will measure the blue, but we will ground the red. Now, by grounding red, ground is never measured, therefore the red channel will not be measured in this configuration. Our test results would be only the current I sub B, and the sum of the currents I sub A and I sub C are guarded and not measured. So here we kind of show a summary of all the test modes and the connections. As we can see, we have the UST measuring the red channel, UST measuring the blue channel, UST measuring both the red and blue, and then we have our various GST or grounded specimen tests as shown in the table here. All right, so why again do we have so many test modes? Well, let's look at a practical example. Let's look at a simple two-winding transformer. So here we have a little two-winding transformer with a little bit of a cutaway looking into the windings. Now, we can kind of represent that in the more simplified drawing here. If we were to go ahead and short the windings on the high side and the low side, basically what we would create is a capacitance between the high side windings and the low side windings, the high side to ground or chassis, and the low side to ground or chassis. So again, we can kind of simplify it in the drawing shown. We can take that simplification one step further, and we would basically look at the insulating system here as capacitance between high and low, high to ground, low to ground. Now, remembering our test modes, let's go through the regimen of testing. So here we're going to do a GST ground, okay? And remember, in GST, ground is always measured. So if we're going to ground the red channel, basically that means we're going to measure it. And anything coming in on the green or the ground lead will also be measured. So we start by applying the potential to the high windings. That creates a current flow that is going to go from the high to the low. Red channel is going to be measured, and it's also going to create a current flowing from high to ground. And once again, ground is always measured in a GST test. The resulting insulation that we are measuring is going to be the capacitance of the high to ground plus the capacitance of the high to low, or the capacitance segments or insulation segments that we see in this diagram. Now, if we want to isolate or examine other components, we run the GST guard anything on either the red or the blue channel, which again means that we will not measure any current coming in on either the red or blue channel. Only the ground will be measured. So here, even though current still flows from high to low, that current bypasses the internal meter, is not measured. The result is we isolate, and we are only measuring now the insulation component of high to ground. And here we show the ungrounded specimen test, or the UST, where we're going to then measure on the red channel. Since it is a UST test, ground, or the green lead, is always guarded and never measured. So again, we apply the potential on the high side windings. We create the current flow through the C high to low. That is going to be measured, and the current that is flowing from high to ground will be guarded. So again, we've isolated and we are now only looking at the high to low insulating component. And then we basically repeat all the tests, but we now apply the potential to the low side and measure to the high side. But we repeat all of the tests that were previously run. So again, the GST ground all. We now measure the low to high combined with the low to ground insulation components. The GST guard the red or the blue. Once again, we've now isolated and we're only looking at the low to ground component. And finally, the UST red, where now we are only looking at the low to high component. All right, let's look at another example. Let's take a look at a 6-terminal motor stator. So here we kind of show the motor stator is made up of 3 windings and a total of 6 terminals: T1, T2, T3, T4, T5, and T6. Now that's going to create a relatively complex insulating system. We're going to have capacitance from A to B winding, B to C, C to A. We'll also have capacitance from the A to ground, B to ground, and also C to ground. So again, we can represent it in our triangle here, and we see that we have a little bit more of a complex insulating system going on. But again, the different test modes will allow us to work through and isolate various components so we can analyze the various areas of insulation and determine where the deterioration is occurring. So again, that is the practical reason why we have so many test modes. All right, let's work through some of these. So first thing we do is we short out the windings to get rid of the inductance. And we connect to the chassis ground. Here we'll place one measurement channel on the B winding, one on the C winding, and we will energize or apply our test voltage to the A winding. We'll run the GST ground all. So now we have current flowing from A to C or C to A. We have current flowing from A to B. We have current flowing from A to ground. In essence, we are now measuring the capacitance of A to ground times the sum of the currents flowing from A to B plus A to C. The UST measuring the red. Okay, so now ground is never measured. We're only measuring the current that is flowing on the red channel. So in this configuration, we've isolated and we're now only studying or looking at the current or the insulating component of A to B. Now we simply move our high voltage lead and energize from different perspectives or from the different windings, but we basically repeat the test that we just ran. So the GST ground all. And here we're again looking at the sectors of the insulation, B to ground times the sum of B to C and B to A. In the UST red, we are isolating and only looking at the component of the insulation B to C. And once again, we move our high voltage lead. We energize on the C winding, repeat the test again. So once again, we're running the GST ground, and here we're looking at the C to ground times the sum of C to A plus C to B. The UST R. And once again, we isolate, and now we're only looking at the components of A to C. So once again, you can kind of see that the different test modes simply allow us to isolate different sections of the insulation for analysis purposes to determine where the deterioration and the breakdowns are occurring. Now, interpretation of test results. In the absence of consensus standards dealing with transformer dissipation or power factor values, the NETA Standards Review Council suggests the representative value shown here in the NETA Table 100.3. Now, maximum values for oil are based on data from the Doble Engineering Company. Now, let's talk a little bit about interpretation of measurements, general analysis. We compare to nameplate data, compare to previous test values, so we use this as a trending tool, compare among the phases, review not only the percent power factor, but also current, watts, and capacitance. The percent power factor that is much lower than expected is just as unacceptable as that which is much higher. Again, the change in the power factor suggests a change into the ingredients used in the insulation recipe, as we kind of used in our earlier analogy. A change in current or capacitance of 5% or more is cause for concern. Now, let's also talk a little bit about negative power factor values. Creep currents inside an insulation system, or more commonly on surfaces, create change of potential distribution that may give increased or decreased dissipation factor, and in some cases also negative dissipation factor. This condition is most likely to arise when making UST and GST measurements on specimens who have a capacitive value of a few hundred picofarads or less. Equipment such as bushings, circuit breakers, and low-loss surge arresters fall into this category. The error is usually accentuated if tests are made under unfavorable weather conditions, especially a high relative humidity, which increases the surface leakage. There appears to be no clear-cut way of knowing whether an error is significant or what remedies should be taken to overcome an error. A frequency sweep may give additional information. The best advice is to avoid making measurements on equipment in locations where negative dissipation factors are known to present a problem when unfavorable weather conditions exist, especially high relative humidity. Make sure the surface or porcelain bushings are clean and dry to minimize the effects of surface leakage. Sometimes it's also useful, if we do have to test on a high humidity day, to have fans or high airflow, again, to try to keep the surfaces as dry as possible. Now, make sure that all items such as wooden ladders or nylon ropes are removed from the equipment to be tested and are brought out of the electrostatic interference fields that could influence a measurement. And that concludes our webinar for today. If you like this content, please make sure that you subscribe, hit the like button, ring the bell, to be notified of more content as we post it. Again, this all helps our channel, supports our channel, and again, definitely helps me put together the content. So if you like what we're doing, please hit that subscribe, hit that bell, hit that like. All right. Until next month, be safe out there.